In today's lecture, we are going to discuss a very important concept, and this is actually the concept of four vectors. Actually, you have definitely studied about the four vectors in my lectures in relativistic electrodynamics, but here I am again dealing with the same subject because in this lecture we will see some of the more important four vectors which is needed for your different examinations. So this is just a repetition. In fact, in the previous lecture on Minkowski's four-dimensional space, you have seen the concept of four space, which is also called world space or space-time continuum. You have also learned the Lorentz transformation in terms of the fourth coordinate of the four-dimensional space, which is represented by the symbol x4. So after getting the idea of four space, now we will be able to discuss the concept of four vectors. As you know, when you talk about the three-dimensional Euclidean space, then you have studied in the your in elementary course of physics the vector algebra, where you have discussed the vector in 3D space, and you have seen that if a vector is in 3D space, it has three rectangular components which are commonly known as x component, y component and z component. For example, if there is a vector, let us say A, in a 3D space, then this A is simply written as AXI plus AYJ and plus AZK. You have definitely studied. Here these I, J, K and R are orthogonal unit vectors, you know, along the x-axis, y-axis and z-axis. And these AX, AY and AZ are called the x, y and z components of this three-dimensional vector A. So as in case of the 3D space, you define a three-dimensional a vector which has three components. So just as an analogy, you can say that if our space is four-dimensional and there is a vector in that four-dimensional space, definitely that vector will have four components. Okay? So any vector in four-dimensional Minkowski space or simply in four space is known as four vector. So four vector is what? This is just a vector defined in the four-dimensional space, which is called Minkowski space or the four space or world space, you know. So I have defined here that a vector in 4D Minkowski space or four space is simply called four vector. Okay. In fact, you have learned in the previous lecture the components of a four radius vector, that is the four position vector, how it is transformed from one inertial system to another. Okay. You have learned that actually the four components of a four radius vector are transformed in accordance with the Lorentz transformations. So similarly, any four vector in four-dimensional space follows the same rule of transformation. It means you can say that the components of a four vector also transform from one inertial system to another in a similar manner. That is, these components are also transformed in accordance with the Lorentz transformations. Okay. You have learnt the Lorentz transformation in the previous lecture. I am just repeating it here. You have seen that if the components of the position 4 vector in S frame are in fact x1, x2, x3 and x4, and these components in S prime frame are x1 prime, x2 prime, x3 prime and x4 prime. Okay, I have shown these two inertial systems here. You can see the figure. As usually we consider that this frame S prime is moving along the common x-axis, or here you can say x1 axis, with a constant velocity v. Then if an event in S frame is described by the coordinates x1, x2, x3 and x4, and the same event is defined or specified by the coordinates x1 prime, x2 prime, x3 prime and x4 prime in inertial system S prime, then you know that these x1 prime, x2 prime, x3 prime and x4 prime can be found if you know the coordinates x1, x2, x3 and x4 in frame S. And this is actually done on the basis of Lorentz transformation equations, and you have learnt in very detail these transformation equations in the previous lecture. You know that if we denote the components the components of the 4 position vector in prime frame by the symbol x prime mu, then this x prime mu you have learnt is given as summation over nu from 1 to 4 alpha mu nu times x nu. Okay, and in matrix form you have you can write this equation like this. We write for x prime mu this column matrix. This is x1 prime, x2 prime, x3 prime and x4 prime, and you know this alpha mu nu, this is actually the transformation matrix, and this is a 4 by 4 square matrix, and this matrix is given by this expression. You can see this is gamma 0 0 I beta gamma and 0 1 0 0 0 0 1 0 and minus I beta gamma 0 0 gamma. This is the transformation matrix, and when this transformation matrix is operated on the coordinates x1, x2, x3, x4 of coordinate system S, then this transformation matrix simply transforms these coordinates into the respective coordinates of the S prime frame, which are x1 prime, x2 prime, x3 prime and x4 prime. Okay, this is actually the Lorentz transformation equations in matrix form. Okay, but this transformation is valid only when this condition which I have mentioned here in equation 2 gets satisfied. In fact, we know that this the square of this x mu prime, x prime mu and square of x mu both are actually equal. Okay, only then it means this square of the x prime mu or x mu is invariant under the Lorentz transformation. Okay, when this condition will be satisfied, only then this Lorentz transformation is validated. Okay, now as you know, the 4 position vector or the 4 radius vector, which is denoted by the symbol x mu, is defined as x1, x2, x3, x4. You know these x1, x2, x3, x2 and x3, these are actually the components of this 4 vector x mu in 3-dimensional space. And so this x1, x2, x3 simply represents the position vector in 3D space, which is written by the vector r. And this 4th component, that is x4, which is actually the 4th component of this 4 vector x mu, is equal to ICT. You have learnt this fact in the previous lecture. Okay. I have mentioned it here that you can see these x1, x2, x3 or simply you say x, y, z represent the position vector r of the 3D space, and this x4 which is equal to ICT is the time part of the 4D position vector x mu. Okay. Now in the light of this equation 3, you can now define a 4 vector in general. Actually, x mu is just a proper example of 4 vector. This is known as radius 4 vector or position 4 vector. But any 4 vector is defined on the basis of this equation 3. So in general, if you consider that there is a 4 vector denoted by the symbol a mu, okay, then this a mu will also have 4 components. And these components can be represented by the symbol A1, A2, A3 and A4. So A mu is simply defined as A1, A2, A3, A4, and as in case of x mu, x1, x2, x3 are actually the position vector in 3D space. Similarly, you can say that this A1, A2, A3, all these 3 components are the components of a vector A in 3D space. And this A4, this is the 4th component which is actually the time part of this 4 vector A mu in 4D space. And just as an analogy, we write this A4 as I times AT, where I stands for iota, that is imaginary. Okay. So this is a general expression for any 4 vector defined in 4D space. Okay. Now, as the components of the position 4 vector x mu obeys the transformation law, which is called Lorentz transformation, in a similar way, you can see that the components of this 4 vector a mu will also follow the Lorentz transformation. It means if you know the components of this 4 vector a mu in frame S, which are a1, a2, a3 and a4, then you can easily find what will be the components of this 4 vector a mu in the prime coordinate system, that is in frame S prime. Simply you have to operate the transformation matrix on these components a1, a2, a3 and a4, and you will get the corresponding components of this 4 vector in S prime frame. You can see it here. So as I have told you that if your aim is to find the components of this 4 vector a mu in S prime frame, you can write those components by the symbol a1 prime, a2 prime, a3 prime and a4 prime. And in the similar manner, we represent these components by this column matrix. And this column matrix of a1, a2, a3, a4, these actually represent the components of the 4 vector a mu in the S frame. And you know, when this transformation matrix, this is actually alpha mu nu. When this transformation matrix will be operated on this column matrix a1, a2, a3, a4, you will get the corresponding components in the S prime frame. These are actually the components in S prime frame of the 4 vector a mu, and these are components in the S frame. And when this transformation matrix is operated, then you get these components in S prime frame. And in compact form, this matrix equation is also written like this. This is a prime mu equal to summation over nu 1 to 4 alpha mu nu a nu. Okay. So either by equation using equation 4 or using equation 5, you can easily find what will be the values of a1 prime, a2 prime, a3 prime and a4 prime. Or in other words, you can say using equation 4 or 5, we can easily find the values of a1 prime, a2 prime, a3 prime and a4 prime if we know a1, a2, a3 and a4. Okay. So now let us try to find these components a1 prime, a2 prime, a3 prime and a4 prime. See this matrix or this equation 4, using any equation you can find it. Okay. As I have told you that the position 4 vector defined by the Lorentz transformation is valid when the condition that summation over mu equal to 1 to 4 x mu prime square is equal to summation over mu 1 to 4 x mu square. Okay. So in a similar manner, you can also say that that matrix transformation will be valid only when this condition is satisfied. That is, you can say that summation mu 1 to 4 a mu prime square is equal to summation mu from 1 to 4 a mu square. Okay. Or in other manner, you can write it a prime mu times a prime mu equal to a mu times a mu. Okay. So this equation 4, as I have told you, or this equation 5, using any one equation from these two, we can easily find the components of a 4 vector. Okay. If we know the components of a 4 vector in S prime, then you can find its components in S prime prime by using any of those two equations. Okay. Now we will see some of the important properties of this 4 vector. First of all, we will learn how the square of the magnitude of a 4 vector is obtained. Okay. In fact, when you talk about the square of magnitude of a 4 vector, you can see it is defined as a mu times a mu. This is just the summation mu 1 to 4 a mu square. Okay. And this is defined as a1 square plus a2 square plus a3 square plus a4 square. This is just analogous to the 3D vector. As you know, if there is a vector in 3D space represented by a equal to axi plus ayj plus azk, then you know that mod of a square is simply given by ax square plus ay square and plus az square. Okay. Since this transformation is also orthogonal, so in similar manner you can say that a mu square is simply equal to a1 square plus a2 square plus a3 square plus a4 square. But as you have assumed that this a4 is equal to I times at, so when we will square it, what will be this a4 square? You can see this will be I square times at square. Okay. But I square, you know, this is minus 1. So this is simply minus at square. So instead of this a4 square, I have written here minus a4 square. But some writers or some authors also write this square, that is a square of a mu square from mu 1 to 4 in this manner. That is, this is also written as at square minus a1 square minus a2 square minus a3 square. Okay. Equivalently, you can write this. Any physical condition will not change when you will write the square of a 4 vector in this manner defined in equation 7a. It is equally valid. Okay. Although this expression is not very popular, generally people write the square in this form, but when you will study the higher relativistic theory, particularly you will study the metric element in the different papers of different scientists, you will see that so many scientists use this expression for the metric element. Okay. So this is equally valid. Now, so how we can find the square of the magnitude of a 4 vector you have learned. Okay. Now, see the another property of this 4 vector. Now we are talking about how to find the scalar product of two 4 vectors. Okay. As you know, if there are two vectors in 3D space, first one is equal to A and another is B. Definitely you have studied in your lower classes that the scalar product of these two vectors A and B, which is denoted by this symbol A dot B, this is defined as AX times BX plus AY times BY and plus AZ times BZ. Can you remember? Definitely you have studied. Okay. So just as an analogy, you can say that if there are two 4 vectors, let us say the first 4 vector is A mu and the another 4 vector is B mu. And this A mu is defined by A1, A2, A3, A4. As you know, these A1, A2, A3, these are the 3 components of A mu in 3D space, and this A4 represents its 4th component, that is which is actually the time part of this vector, and this A4 is defined by I times AT. Okay. Similarly, B mu is defined by B1, B2, B3, B4, where B4 is equal to IBT. See, in a simple manner, you can say that A mu has component A1, A2, A3 and A4, and B mu has components B1, B2, B3 and B4. Okay. Just like you can see here that AX, B, AY and AZ are components of the 3D vector A, and BX, BY, BZ are the XYZ components of 3D vector B. So just in the light of this result, that is A dot B equal to AX, BX plus AY, BY plus AZ, BZ, you can see the dot product or the scalar, not dot product but a scalar product you can say, the scalar product of these two 4 vectors A mu and B mu, this is denoted by the symbol A mu B mu. Okay. And it is defined like this: A mu B mu, this will be equal to A1 B1, this is just AX BX, plus A2 B2, this is just AY BY, and A3 B3, and as here there is 4th coordinate, 4th component 2, so there will be plus A4 B4. But what will be this A4 B4? You can see when you say A4 times B4, sorry, the page has been turned, but this will be just okay. This is just a demerit of my device, this has been occurred, but it will be corrected soon. So you can see A4 times B4. As you can see, A4 is equal to what? This is I times AT, and B4 is I times, this is AT, BI times BT. Now I times I, this will be I square, and AT times BT, but you know I square is equal to minus 1, so this will be equal to simply minus AT times BT. Okay. So instead of A4 B4, I have written here minus AT BT. Okay. So the scalar product of two 4 vectors A mu and B mu is simply defined by the product, the sum of the product of corresponding components. That is, you have to take the first component of A mu and the first component of B mu and multiply. Again, we take the second component of A mu and second component of B mu and multiply. And in this way, we will add the first 3 components and first 4 components. Okay. So this is the technique how you will find the scalar product of two 4 vectors. Okay. Now we will explain a very important product of a scalar very important property of a scalar product of two 4 vectors. This property says that the scalar product of two 4 vectors is invariant under Lorentz transformation. Okay. The scalar product of two 4 vectors is invariant under Lorentz transformation. When you say that the scalar product of two 4 vectors is invariant under Lorentz transformation, what does it mean? It means you have to show that if the two 4 vectors in S prime frame are in fact A prime mu and B prime mu. These are the two 4 vectors in S prime frame. Okay. Or you can say that the A prime mu and B prime mu are actually the components of two 4 vectors in S prime frame. And at the same time in frame S, these vectors are A mu and B mu. Then if you say that the scalar product of these two 4 vectors is invariant under Lorentz transformation, that means you have to prove, you have to show that A prime mu times B prime mu is equal to A mu B mu. Okay. You can see I have not written the sign of summation here because mu is a repeated index, and that's why summation is not in fact needed here. Now you know that A prime mu times B prime mu, how it is defined? Just we have learnt. This will be defined as A1 prime times B1 prime plus A2 prime plus B2 prime plus A3 prime times B3 prime plus A4 prime times B4 times. This is just the definition of a scalar product of two 4 vectors. Now, if you want to find the value of this product A prime mu times B prime mu, you have to evaluate all these 4 components, not only 4 but 8 components. A1 prime, A2 prime, A3 prime and A4 prime. These are 4 components of A prime mu. And you have also to find the values of B1 prime, B2 prime, B3 prime and B4 prime. How we can find these components? As you have learnt, these are actually the components of a 4 vector in S prime frame. So if we know the components of these vectors in S frame by using the transformation equation or the Lorentz transformation equation, you can easily find what will be these components. As I am just repeating the things, you have learnt that if this column matrix A1, A2, A3, A4 represent the components of the 4 vector in S frame, okay, and its components in S prime frame are represented by the column matrix A1 prime, A2 prime, A3 prime and A4 prime, then this matrix is equal to the product of this transformation matrix and this column matrix. Or in other words, you simply say that this transformation matrix is an operator. When this transformation operator, that is alpha, mu, nu, will be operated on this column matrix, we will get simply A1 prime, A2 prime, A3 prime and A4 prime. Okay. Now you can see how this how these components can be found. Let us see here. If you want to find the value of A1 prime, see here, we will take gamma times A1. So this is gamma A1, okay? 0 times A2. So this is 0 times A2. 0 times A3. This is 0 times A3. Plus I beta gamma times A4. So this is plus I beta gamma times A4. Now this will be simply equal to gamma times A1 plus I beta A4. Okay. Now when you will find A2 prime, that will be 0 times A1, that will be 0. 1 times A2, that will be A2. 0 times A3 and 0 times A4, all will be 0. So simply we will get A2 prime equal to A2. You can see I have done it here. In fact, as you have calculated the value of A1 prime, so in the light of this equation, you can simply say that in similar manner we can find B1 prime, and that B1 prime will be equal to gamma times B1 plus I beta B4. Okay. Now as you can see from that matrix, A2 prime will be 0 times A1 plus 1 times A2 plus 0 times A3 plus 0 times A4, and that will be simply equal to A2. So similarly, in the same manner, you can say that B2 prime will be equal to B2. Now when you will find A3 prime, that will be 0 times A1 plus 0 times A2 plus 1 times A3 plus 0 times A4, and that is simply equal to A3. Okay. I am not turning the page to show that matrix because definitely that matrix is in your mind. Now in the similar manner, you can say that B3 prime is equal to B3. Now when you will find A4 prime, you can see how this A4 prime will be obtained. I am writing it here. A4 prime, you can see this will be minus I beta gamma times A1. Okay. This minus I beta gamma times A1. Okay. Plus 0 times A2. See the matrix. Plus 0 times A3. Okay. And plus last term, this will be gamma times A4. Okay. So these two terms simply are 0, and so this will be equal to gamma times A4 minus I beta A1. I beta A1. Okay. And you can see I have obtained it here. This A4 is equal to gamma times A4 minus I beta A1. And in the similar manner, we can say that B4 prime will be gamma times B4 minus I beta B1. Okay. So in this way, using that transformation matrix, we have obtained all the components of the 4 vector A mu and B mu in S prime frame. Okay. Now we will substitute all these values in this equation 9. We have obtained A1 prime, B1 prime, A2 prime, B2 prime, A3 prime, B3 prime, A4 prime and B4 prime. Now substitute all these values. So for your convenience, I have just repeated that expression here. Okay. So A prime mu times B prime mu, this is equal to A1 prime B1 prime plus A2 prime B2 prime plus A3 prime B3 prime plus A4 prime B4 prime. Now substitute the value. We have seen that A1 prime, this is equal to gamma times A1 plus I beta A4. Okay. And B1 prime, this is gamma times B1 plus I beta B4. Since both of these equation contains gamma, so gamma times gamma will be gamma square. Okay. Now you have seen that A2 prime is equal to A2 and B2 prime is equal to B2. So A2 prime B2 prime will be simply equal to A2 B2. You have also seen that A3 prime is equal to A3 and B3 prime is equal to B3. So A3 prime B3 prime will be simply equal to A3 B3. Okay. But what is A4 prime and B4 prime? You have just seen that A4 prime is equal to this much. This is gamma times A4 minus I beta A1 and B4 prime is this much. Since both of these quantities contain gamma factor, that is Lorentz factor gamma, so there will be gamma square times this and this. Okay. So let us see here. I have written this is actually equal to gamma square A4 minus I beta A1 times B4 minus I beta B1. Okay. Now let us simplify this equation a little bit. This gamma square you can see is at each. This is written just in the similar manner. Now we will take the product of these two factors, that is A1 plus I beta A4 and B1 plus I beta B4. See, A1 times B1. So here there is A1 B1. Now take I beta A4 times I beta B4. I times I square, which will be minus 1. So you can see here I have written minus. Beta times beta, this will be beta square, and A4 B4. A4 B4. Okay. Now we will multiply A1 by I beta B4 and B1 by I beta A4. In both of these two terms, I beta is a common factor. So I beta has been taken as a common factor and the remaining terms are A1 B4 plus B1 A4. Okay. Now these two terms has been written just like above. Okay. Now see the last term. Here there is gamma square at each. And we will now take the product of A4 minus I beta A1 and B4 minus I beta B1. So let us see. This will be A4 times B4. I have written it here, you can see. Again, you will take the product of minus I beta A1 and minus I beta B1. Minus minus will be plus. I square will be again minus. And this is beta square A1 square. So this is beta square, not A1 square, beta square A1 B1. So beta square A1 B1. Okay. Now take the product of this A4 with minus I beta B1 and this B4 with minus I beta A1. You can see minus I beta will be a common factor and the remaining terms will be A1 B4 plus B1 A4. Okay. Now you can see this term minus I beta A1 B4 plus B1 A4 and this term I plus I beta A1 B4 plus B1 A4. These two terms will cancel out. Have you understand or not? Gamma square is common and both one term is positive and another is negative. So these two terms will cancel out. Now see here. This gamma square times A1 B1. Okay. And gamma square times gamma square times beta square A1 B1 with negative sign. I am marking this by cross sign here. Combine these two terms. These two cross terms we will now combine. You can see. Actually, gamma square A1 B1 will be as a common factor and in first term there will be 1 now and in the second term this minus beta square remains. So combining these two crossed terms you can write gamma square A1 B1 times 1 minus beta square. Okay. Now again we will associate these two terms. which I am just marking by this dot symbol. You can see the algebra. Here there is in fact gamma is minus gamma square beta square a4 b4, and in the second term there is plus gamma square a4 b4. So again gamma square a4 b4 from these two dotted terms can be taken as a common factor. You can see I have taken this gamma square a4 b4 as a common factor. So in this lower term 1 will remain, and in this upper term beta square will remain with negative sign. Okay. Now you know that gamma is equal to 1 over root over 1 minus beta square. So gamma square is equal to 1 over 1 minus beta square. So 1 minus beta square, this will be equal to 1 over gamma square. So instead of this 1 minus beta square, I have written here 1 by gamma square. And also in the last term, this 1 minus beta square has been replaced by 1 by gamma square. Now this gamma square and this gamma square will cancel. This gamma square and this gamma square will also cancel. So what are the remaining terms? You can see these are a1 b1 plus a2 b2 plus a3 b3 plus a4 b4. And this product can be written as a mu b mu from the definition of the scalar product of two 4 vectors. So what you are seeing here, we have started with the product of a prime mu and b prime mu, and you can see this product is simply equal to a mu b mu. So you can say that this a prime mu times b prime mu is equal to a mu b mu. This is actually the scalar product of two 4 vectors in S prime frame, and this is the scalar product of the same two vectors in S frame, and these two scalar products are equal. So we can simply say that the scalar product of two 4 vectors is invariant under Lorentz transformation. Okay, I think you have clearly understood how this fact can be explained. So you have seen that we have dealt with the concept of 4 vector in very detail. What is a 4 vector? What are its important properties? You have learnt all each and every aspect of this 4 vector. Now in the forthcoming lecture, we will see the important examples of some 4 vectors. For example, we will learn about the velocity 4 vector, the momentum 4 vector, the acceleration 4 vector, and the force 4 vector. We will deal with in the forthcoming lecture. I hope you have definitely enjoyed this lecture, and this is very important for you. Definitely you should watch this video very seriously, and I will suggest you write all these facts in your notebook and revise it. Definitely all these things will be yours.